name is Pavel Safronov of Edinburgh, who will speak about the local structure of Lagrangians and shifted Poisson geometry.
Thanks for inviting me. Yeah, unfortunately, I couldn't be there in person. Okay, so I want to give somewhat of an overview of a relationship between some derived and maybe higher structures, so shifted Poisson geometry, and very classical classical symplectic geometry and some phenomena that appear there. Okay, so let me begin with something that everybody is familiar with, which is, let's start with some symplectic manifold X and some smooth Lagrangian. And at first, let me consider the case of just C-infinity manifolds. So you have X, a symplectic manifold, and L, Lagrangian submanifold. So there's a well-known theorem due to Weinstein that there's a neighborhood of a Lagrangian which is symplectomorphic to a neighborhood of the zero section of that Lagrangian. So locally near a Lagrangian, all symplectic manifolds look the same. Okay, so this is quite an important theorem. But if you try to look for an analog of this theorem in a holomorphic setting or algebraic setting, then it turns out to be false. And it's kind of fails dramatically. But what I want to explain is that it fails in an interesting way. When I say fails dramatically, so the usual Lagrangian neighborhood theorem is stated about tubular neighborhoods, so the actual open neighborhoods. Maybe something stronger than an, or something that's even smaller than an open neighborhood is a formal neighborhood. So you can ask, is there a formal neighborhood? And maybe even something weaker, you can ask for, is there even a first order neighborhood where this holds? And it turns out that it fails in the strongest possible sense. So even when you talk about first order neighborhoods. So here's some example. If you have an elliptic K3 surface, so you have a holomorphic symplectic manifold S of real dimension 4, so complex dimension 2. So it's a complex surface. And it's fibered over P1, and generic fibers are elliptic curves. Because you're talking about curves inside of a surface, inside of a symplectic surface, an arbitrary curve will be Lagrangian. So the fibers of this map F will be Lagrangian. But then if you look at the generic fiber, you can't find even a first order neighborhood where an analog of this statement holds, that the neighborhood of the fiber is symplectomorphic to first order neighborhood of the fiber inside of its cotangent bundle. Okay. And so my goal will be to try to quantify how, to which extent this theorem fails, and try to relate this to some derived symplectic structures. Okay, so if you want to start proving the Lagrangian neighborhood theorem, so the first thing is to even find a tubular neighborhood. So you want to look at the normal sequence for the submanifold. So you have the tangent bundle of the submanifold, the tangent bundle of the ambient manifold restricted to the submanifold, and then the normal bundle. And because L is Lagrangian instead of X, the normal bundle will be isomorphic to the cotangent bundle. So the first thing you want to do is you want to split the sequence. So you want to embed the normal bundle into the ambient manifold X. And there's an abstraction to doing this, which is a cohomology class. So you can look at an extension class for this sequence. So you'll have an extension class in the first cohomology of L with coefficients in sim2 TL. So maybe a priori you would expect to get a class in H1 of L with coefficients in TL tensor TL. So maybe a priori it's really a class here. But because L is Lagrangian, this class happens to be symmetric. Okay, so all right, so there's this interesting class. Of course, if you're working with C-infinity manifolds, this cohomology group will vanish. But if you're working with algebraic manifolds or holomorphic manifolds, this cohomology group might not vanish, and this class might not vanish. So this is what's happening in this example I mentioned, that you have a non-vanishing extension class like this. Okay, so out of this sort of simple situation of Lagrangian in a symplectic manifold, you get an interesting extension class, an interesting cohomology class. So what can you do with this class? Something that people do, but something that I will not be talking about, is that this extension class actually gives you a special Kähler structure on the moduli space of holomorphic Lagrangians. So for instance, if you have a Lagrangian fibration on a hyperkähler manifold, so holomorphic Lagrangian fibration, on the base, there will be a special Kähler structure. And that special Kähler structure is encoded by this extension class, essentially. So this is due to Hitchen, Dohnanyi-Markman, and others. But instead, I want to interpret this in a different way. So if you look at this class, maybe let's first ignore the fact that there's some cohomology group happening. So if you just think about a class in H0 instead of H1 of L with coefficients in wedge 2 TL, then you would expect that to be a Poisson structure. So this extension class kind of looks like a Poisson structure, except it involves the first cohomology, and instead of exterior algebra, you have symmetric algebra. So what I want to explain is that this extension class is actually a part of a -1 shifted Poisson structure on the Lagrangian L. Okay, so even though here I'm talking about very classical geometry, there's nothing derived happening. There's already an interesting shifted Poisson structure around. Okay, so let me briefly remind you the setting of shifted symplectic structures. So we've already seen mentions of that in talk by Francis Bischoff. So I will not be very precise, but let me just fix the setting. So I will be working in the setting of derived algebraic geometry. So X is some sort of derived object. Let's say it's some derived algebraic stack. And so Pontiff-Toen and Bakevitz-Ozzy, they introduced the notion of a n-shifted symplectic structure. And if you ignore various details, so it boils down to providing a two form. So it's a section of wedge 2 of the cotangent bundle of X, except it's a section of some non-trivial cohomological degree. So it's element of Hn of wedge 2 T star. And then there's, just like for usual symplectic structures, usual symplectic structure is a two-form satisfying closure condition and satisfying non-degeneracy. So in this case, non-degeneracy is a generalization of the usual non-degeneracy. So out of the two-form, you can cook up a map from the tangent to the cotangent bundle. Because this two-form has a non-trivial degree, it has degree n, you get a map from the tangent bundle to a shift of a cotangent bundle. And you want this to be an isomorphism. So here I'm talking about tangent bundles of derived stacks. So these are really complexes of vector bundles, and I want this to be a quasi-isomorphism of complexes of vector bundles. But I will not be that detailed in this talk. And then the closure condition, so you want to say that the two-form is closed. Because you're working in this kind of homotopical context, you want to say it's closed up to coherent homotopy. What this means explicitly is that there are homotopies witnessing the closure condition. So if you look at the Durand differential applied to this two-form, it's not going to be strictly speaking zero. There's going to be a homotopy saying that that three-form is actually zero. And then there are further conditions that homotopy itself is closed. And again, there's a further homotopy witnessing that condition. And there's this infinite sequence of equations. Okay, so that's roughly speaking what n-shifted symplectic structure is. And another notion I want to mention is the notion of an n-shifted Poisson structure. So they were introduced by Kalak, Pantev, Toenva-Kevitsozzi. And it's very similar. So there, I can't say this uniformly, but in the case when n is even, so for instance, n is 0, then you're just looking at homology classes so a bivector, but of a non-trivial cohomological degree. So h minus n good coefficients in wedge 2 of the tangent bundle. And then in case when n is odd, it's actually a symmetric bivector rather than alternating bivector. And again, you want to say that the integrability holds of the Poisson structure. So the bracket of the bivector with itself is 0. But you're working in this homotopical context, so the bracket is 0 up to coherent homotopy. So just like for shifted symplectic structures, the bracket of the bivector with itself will be a certain trivector. And then you want to say that that trivector is 0. You want to provide that homotopy, that's pi3. You want to provide further homotopies for integrability. There's a 4 vector and so on, witnessing further integrability conditions. So I want to point out that these homotopies are actually quite interesting. So in my talk, I'll mention some of them. Namely, okay, usually you wouldn't think of a homotopy as something concrete, but if the bivector pi2 is 0, you might still have a non-trivial Poisson structure. So this homotopy pi3 might be non-trivial even though pi2 is 0. But then if you think what is this trivector, it's going to be homotopy from 0 to 0. So in other words, it's still a cohomology class. So if you know that pi2 is 0, then the trivector is an honest cohomology class. And so for instance, if n is even, it's going to be this element in some cohomology group of degree minus 2n minus 1, coefficients in wedge 3, tx, and then and it's odd, then this is symmetric. Okay. All right, so this is sort of the basic basic two notions for this talk: shifted symplexic structures and shifted Poisson structures. A relationship between them is just like in the classical context. If you have a shifted symplexic, ordinary symplexic structure, you can invert that two form and get a bivector. And the claim is that you can do this in the derived context as well with this shifted symplexic structures. So this was proved by Kalak, Pantyev, Toin, Vekevitsozzi, and independently Pridham, that you can invert an n-shifted symplexic structure to get an n-shifted Poisson structure. Okay. So pretty much all theorems you think are true are actually true, except maybe the proofs are a bit more complicated. Right. So another notion that I want to mention is that there's a notion of a Lagrangian submanifold for n-shifted symplexic structures. So if you have some map from L to X, so X is some derived algebraic stack with an n-shifted symplexic structure, and L is again some derived algebraic stack, you can talk about Lagrangian structures. So usually you would say being a Lagrangian is a condition. You want to say that the restriction of the two form to Lagrangian is 0. Well, in this context, we remember all the homotopies. So we'll actually define some data. The data will be that null homotopy that witnesses that the restriction of the two form to the Lagrangian is 0, together with higher homotopies relate to closure. Then there's a non-degeneracy condition on this null homotopy. So out of this null homotopy, you can cook up a map from the normal bundle to the cotangent bundle. And just like in classical symplectic geometry, so one way to say a Lagrangian submanifold, you can say half-dimensional, but a fancier way to say a Lagrangian submanifold is that out of a two form, you can cook up this map from, so once you know it's isotropic, you can cook up this map from the normal bundle to the cotangent bundle, and you want to say that that map is an isomorphism. So same thing here. Okay. And the theorem that I want to, so basically my whole talk will be about providing examples for this theorem. Okay, so the theorem proven by Milani and myself is that if you have an n-shifted Lagrangian structure, then on the source, so on the Lagrangian itself, there's a natural shifted Poisson structure over shift one less. So again, we've seen an example of this principle in Francis's talk. So there was some Lagrangian map obtained from on a moduli space of flat connections, and then on the source there was a shifted Poisson structure. So that's an example of that. Okay, so let me say a word about the proof. So the proof is very similar to the proof of the first theorem. In fact, it's modeled after that. So just like you can invert shifted symplexic structures to get shifted Poisson structures, there's a notion of coisotropic structures that we introduced with Milani. And we actually explain how to invert a Lagrangian structure to get a coisotropic structure. And then if you look at the definition of a coisotropic structure, so again, there's a coisotropic structure on this map from L to X. One part of the data is going to be an n-shifted Poisson structure on X, but another part of the data will be an n-1 shifted Poisson structure on L. And so if you forget about that coisotropic structure and just remember the Poisson structure on L, that's what the theorem is saying. Okay, and the example that I started with is that you have a Lagrangian submanifold, L inside of X. So in this case, you look at zero-shifted symplectic structures. So X is ordinary symplectic manifold. So n is 0. So in this case, on the source, you will get a -1 shifted Poisson structure. And the bivector of that -1 shifted Poisson structure is that extension class that I talked about. All right, so the rest of my talk is just going to be about examples of application of this theorem. So I'm going to give you some Lagrangian, and I'm going to explain what is an interesting Poisson structure on the source. All right, so the first example is in the context of groupoids. So let's say you have a symplectic groupoid, G over X. So that means that, well, you have a groupoid on X, and on the groupoid itself there's a 2 form with a symplectic structure, omega. The symplectic structure is multiplicative groupoid structure, and the unit section is Lagrangian. Okay. So something you can extract out of that, if you look at the normal bundle.
Pavel, sorry to interrupt. I think there's a question in the chat. I don't know if you can see it.
Yeah. So Dima Rotenberg is asking about shifted Poisson structure and derived critical locus. In this convention, it's -1 shifted symplectic or -1 shifted Poisson. So it's -1. I will talk about this example at the end. So derived critical locus of a function will be -1 shifted symplectic. All right. Okay, so yeah, so you have this symplectic groupoid. So if you look at the normal bundle of the unit section, that's exactly the Lie algebroid. But because it's Lagrangian, the normal bundle of the unit section is also the cotangent bundle of X. I think there's someone is not muted in the chat. Yeah. Right. Okay. So so in this case, the Lie algebroid underlying the symplectic groupoid is the cotangent bundle. And so if you look at the anchor map, it can be a map from the cotangent bundle to the tangent bundle of X. And out of this, you can extract a Poisson structure. So that's pairing with the Poisson structure. And so what we usually say is that this symplectic groupoid is an integration of the Poisson structure. Okay, so how does this relate to the theorem I mentioned before? You can encode the data of the symplectic groupoid in terms of a one-shifted Lagrangian structure. Namely, if you look at the quotient stack, X mod G, this quotient stack has a one-shifted symplectic structure. And the quotient map from X to the quotient stack has a Lagrangian structure. Okay. In fact, this is a one-to-one correspondence. If you have a Lagrangian structure, one-shifted Lagrangian structure on this map, that's the same as providing the data of a symplectic groupoid. And the claim is that if you look at now you have a one-shifted Lagrangian structure. So on the source, you'll have a zero-shifted Poisson structure. So an ordinary Poisson structure on X. The claim is that that's exactly the Poisson structure that you recover in the usual way from a symplectic groupoid. Okay, so just via this construction. Okay, so that's one sort of easy example.
Pavel, there's a question. Just in a second.
Just a stupid question, just to understand. Is this correspondence, in the simpler terms, is a relation between the classical Cazul brackets on differential forms and the corresponding Poisson structure? The Cazul bracket is a well, in your language, it's shifted Poisson structure, which is actually odd Poisson structure, and Poisson structure is Poisson structure. Can be understood in this way.
I haven't quite absorbed the question, but maybe I can try to think about this. Maybe you can say more details after the talk. I'm not quite sure.
Yeah, I'll just repeat. So this shifted. Oh,
He asked you to ask him the question after the talk. Okay. Good. Thank you.
we may still repeat, Ezra.
No, he doesn't want you to repeat it.
Yeah, we can discuss after the talk, but I wanted to make the question clear to the audience. Thank you, Ezra. So I will repeat. So I'm speaking about the relation with classical Cazul bracket and the Poisson bracket. Thank you.
Mm-hmm. Okay. Yeah, maybe I'll try to address that in the last 10 minutes when we have questions. All right. Yeah. So the claim is that out of this one-shifted Lagrangian structure, you get ordinary Poisson structure in the source. Okay. So let me move to something slightly more derived. But let's say you have a complex manifold. If you have a complex manifold, in general, there are no holomorphic connections in a tangent bundle. And there's an abstraction class for this defined by Tia, which lives in some cohomology group. So the first cohomology group with coefficients in the tangent bundle tensor sim2 of the cotangent bundle. And then this abstraction class vanishes if and only if there is a global holomorphic connection on the tangent bundle. So if you actually say symmetric sim2, then you actually get a torsion-free connection. So, okay, so you have this interesting class called the Itea class. And what was realized by Kapronov is that this Itea class is a part of a bigger structure. Namely, this Itea class is actually a Lie bracket underlying an L-infinity structure on the shifted tangent bundle. So if you look at the shifted tangent bundle, so Tx minus 1, in the derived category of coherent sheaves on X, then the claim, so what is shown by Kapronov is that there is a natural L-infinity structure. And if you look at what is the Lie bracket of this L-infinity structure, so first of all, what is a Lie bracket on such a gadget? Well, it's a map from wedge 2 of the Lie algebra to the Lie algebra. But because you have wedge 2 of something shifted, you can take it outside to get sim2 because of the shift and because of the sign rule. So this map is the same as a map from sim2 Tx to Tx shifted by 1. And if you think of what is such a map in the derived category, such a map in the derived category is exactly a cohomology class like this. So in this sense, the ITA class, so this L-infinity structure extends the ITA class. Okay, so this is what happens for a general complex manifold. But now let's say this complex manifold also has a symplectic structure. And what I mean is that it has a holomorphic symplectic structure. So in this case, what you can do is you can use the symplectic structure to identify a cotangent bundle with a tangent bundle. So you'll get an element of Tx tensor sim2 Tx. So the first claim is that this element is actually completely symmetric. So this ITA class in the symplectic setting will actually be an element of H1 with coefficient sim3 of the tangent bundle. And furthermore, there is a relation for this symplectic ITA class. Namely, you can just generalize the usual bracket of polar vectors to symmetric polar vectors, and maybe cohomology of X with coefficients in symmetric polar vectors. And so the Poisson bracket of this ITA class with itself will be some 4 vector. And because the ITA class itself had degree 1, this bracket will actually be of degree 2. So you'll get a class in H2 of X with coefficients in sim4. And it claims that that's actually 0. So that's sometimes called IHX relation. But if you think of this in a derived way, so what's happening is that this relation kind of looks like this ITA class looks like a trivector underlying a -1 shifted Poisson structure. And the fact that you have this IHX relation tells you that this bracket of pi3 with itself is 0 up to homotopy. And what I want to explain is that in this case, this symplectic ITA class is actually a part of a -1 shifted Poisson structure. So this -1 shifted Poisson structure has pi vector being 0, but there's a non-trivial trivector and higher polar vectors. And the trivector is exactly the symplectic ITA class. All right. So let me, okay, so how does this work? So in general, if you have some L-infinity algebra, G, you can encode the data of an L-infinity algebra into a differential, the Chevalier-Algebra differential, on the Chevalier-Algebra complex. So the symmetrical algebra of G dual shifted by -1. Now, if you have a non-degenerate pairing on the Lie algebra, and this non-degenerate pairing is compatible with brackets, so this is actually a cyclic L-infinity algebra. So using this non-degenerate pairing, you can endow this symmetric algebra with the Poisson structure. So it's a constant Poisson structure. And in this case, the Chevalier-Algebra differential is actually Hamiltonian. So there's a potential for this vector field. And so this phi potential. And the Chevalier-Algebra differential is actually given by a bracket, by the Poisson bracket with this potential. So this phi is the potential of the cyclic L-infinity structure. Okay. And so if you just look at Kapran's paper and you just slightly rephrase it in modern terms, what you see is that this in the symplectic case, this Lie algebra, the shifted tangent bundle, is actually a cyclic L-infinity algebra. And the potential for this L-infinity structure is some -1 shifted Poisson structure. So if you unpack what it means to be a potential, in this case, it's really some element of, roughly speaking, x with coefficients in sim tx, maybe at least 3. So the claim is that that potential is a -1 shift of the Poisson structure. And the way this -1 shift of the Poisson structure arises is that you just look at the diagonal Lagrangian. So you look at x embedded as a diagonal in x cross x. Okay, so this is an ordinary Lagrangian, there's 0 shift Lagrangian. So on the source, there is a -1 shift of the Poisson structure. Okay, and again, the symplectic Atiyah class is the trivector of that -1 shift of the Poisson structure. Right, so that's another example. Let me switch to something else. Let me switch to the land of Poisson-Lie groups. And so let's say you have a Poisson-Lie group. So we've seen Lie bialgebras in the previous talk, and these are integrated versions of Lie bialgebras. So Poisson-Lie groups often come as a part of a triple of groups. So you have the double D. It's some Lie group together with a non-degenerate pairing on its Lie algebra. So symmetric non-degenerate pairing. And then the group G, the original group G, is embedded as a Lagrangian subgroup. But in addition to that, there is a Poisson-Lie dual group, G dual, also inside of the double, which is also Lagrangian. And at least on the level of Lie algebras, the two are transverse. Okay, so these are transverse Lagrangian subalgebras of the Lie algebra of the double. Okay, so now if you look at this Poisson-Lie dual group, G dual, and if you look near the unit in the Poisson-Lie dual, the Poisson structure to first order looks exactly like the usual Kirillov-Kosten-Surya Poisson structure on the dual of the Lie algebra at the origin. So they both vanish at the origin, and to first order, they agree. Okay, and a question that many people have worked on, in some cases the answer is yes, in some cases the answer is no, is whether there's a Poisson isomorphism of neighborhoods of the unit in the Poisson-Lie dual and the origin in G dual. Maybe, again, you can ask this question about actual neighborhoods, or you can ask this question about formal neighborhoods. Okay, and so I will not answer this question, but I'm just going to explain what is the abstraction in terms of shiftless symplectic structures. So what is an abstraction to have this formal linearization result? So something you can cook up out of this setting. So classically, you would cook up a double symplectic groupoid. I will just care about a certain piece of this double symplectic groupoid. And this will give rise to a certain one-shifted symplectic stack. So if you take the double D and take a double quotient by G on both sides, the claim is that there's a natural one-shifted symplectic structure on that. And if you look at the inclusion of the unit, so point inside of the double, so point mod G inside of this double quotient, there's an actual Lagrangian structure. Okay. Well, and the claim is that okay, so now you have a one-shifted one-shifted Lagrangian structure on the map, so you can extract a zero-shifted Poisson structure on the source. The claim is that this zero-shifted Poisson structure exactly gives you an abstraction to find a formal linearization of G dual. Namely, this Poisson Lie group G dual is formally linearizable at the unit if and only if the corresponding zero-shifted Poisson structure is 0. In fact, the claim is a little bit stronger. There's a groupoid of shifted Poisson structures, and really a null homotopy of this zero-shifted Poisson structure gives you a formal linearization. So there's a one-to-one correspondence. Okay. So let me get to the final example. And that's going to be, again, for a different shift. And this is going to be in shift -1, coming from the derived critical locus that Dima Reutenberg mentioned. Okay, so let's say you have some smooth algebraic variety, X, and some polynomial function on that variety, W. So something people are interested in is this category of matrix factorizations. So it's a certain DG category. It's Z2 graded. So there's only 2 terms, and it's kind of periodic. And this DG category of matrix factorizations consists of diagrams. So you have 2 coherent sheaves on X, V1 and V0, connected by differentials. So there's a differential from V1 to V0 and from V0 to V1. The differential does not square to 0, but the differential squares to multiplication by W. So in a sense, it's a factorization of W into a product of 2 maps. Okay, so that's the category of matrix factorizations. And it's sort of well known that this category of matrix factorizations has something to do with the critical locus. So there's many statements about this. For instance, this category is supported only on the critical locus. So it only sees the formal neighborhood of the critical locus of the function W. Okay, so now let's look at this critical locus, and let's consider a special case when the critical locus of this function is actually smooth. So let me call this critical locus Y. So in this case, one refers to W as a Morse bot function. So it would be a Morse function if the critical locus is actually consists of points. But in this case, it's smooth. So this is a Morse bot case. So something you can do is you can look at the normal bundle of the critical locus inside of the ambient variety, Y instead of X. And this normal bundle has a natural quadratic form given by the Hessian of W. So this Hessian is well defined because you're on a critical locus, and it's non-degenerate due to this Morse bot condition. It gives you a quadratic form on the normal bundle. Well, when you have a quadratic form on the vector bundle, you can extract the corresponding Stiefel-Whitney classes. So I'll only care about the first 2 Stiefel-Whitney classes of this quadratic bundle, W1 and W2. And so something you can do is you can look at the derived category coherent sheaves on Y twisted by these classes. So you can think of W2 as prescribing a gerb. And so you can look at coherent sheaves twisted by this gerb, which is W2. W1 gives you a Z2 principal bundle. So what you can consider is you can consider these two periodic complexes, which are graded not by element of Z mod 2, but by element of that principal bundle. Okay, so that's this twisted derived category. And so Kapustin, Rosansky, and Saulina, they conjectured a relationship between the category of matrix factorizations in this Morse-Bott case and this twisted derived category. And this was corrected by Telemann somewhat recently. And the correction is again interesting. I want to explain what is the geometric meaning of this correction. So the claim is that the category of matrix factorizations in this Morse-Bott case is not the category of coherent sheaves on the critical locus, but it's a deformation of this category along some Maurer-Cartan element. So there's a certain polar vector on Y, which satisfies a Maurer-Cartan equation, and polar vectors allow you to deform the category of coherent sheaves. And the claim of Telemann is that this deformation exactly gives you the category of matrix factorizations. Okay, so I want to explain the sort of symplectic geometry of this setup. Okay, so out of a potential, like I can extract different kind of geometric objects. I can look at the ordinary critical locus. So just a subscheme of X, which might be singular, but I'm interested in the Morse-Bott case, so this is going to be a smooth subscheme. So this is ordinary critical locus. The other thing you can consider is the derived critical locus. So you can consider the derived scheme, which is the derived critical locus. And this derived scheme will be equipped with a -1 shifted symplectic structure. So that's sometimes referred to as the BB bracket. Or the corresponding -1 shifted Poisson structure is the BB bracket. And there's a natural map from the ordinary critical locus of the function to the derived critical locus. So this map doesn't have to be an isomorphism. Namely, so the derived critical locus is given by some Cazul complex, and only when this Cazul complex is exact, this map will be an isomorphism. So only when you get a regular sequence, it's going to be an isomorphism. Well, the claim is that it's actually, there's an interesting geometry underlying this map. So if you assume that you're in a Morse-Bott case, so the critical locus is smooth, then this map from the critical locus to the derived critical locus has a Lagrangian structure. So in this case, it's a -1 shifted Lagrangian structure. On the target, you have a -1 shifted symplectic structure. So here you have Lagrangian structure. And really, in this case, it's a property of this map. It's easy to show that if there's a Lagrangian structure, it's unique. Okay, and so now you can, again, try to apply the original theorem. So you have a -1 shifted symplectic, -1 shifted Lagrangian structure. So on the source, you'll have a -2 shifted Poisson structure. And this -2 shifted Poisson structure is exactly this Maurer-Cartan element that Telemann used to deform the category of coherent sheaves. So usually you might think about deforming category of coherent sheaves along an ordinary Poisson structure. But in this case, everything is happening in the Z2 periodic world. So it doesn't matter whether it's -2 shifted or 0 shifted or 2 shifted. So what's important is that it's evenly shifted. Okay. And so I will not maybe comment on the rest of the slide. So if you're interested, you can ask me about that. So there's some this result is a part of a bigger program that some people are developing of attaching some Z2 two periodic DG categories to -1 shifted symplectic schemes. So in this case, this claim about Lagrangians that you have critical locus inside derived critical locus, it's a -1 shifted Lagrangian, actually tells you that the derived critical locus is not quite -1 shifted Lagrangian bundle of the ordinary critical locus, but it's a deformation of that using the -2 shifted Poisson structure. Okay, I'll stop here. Thanks.
Thank you very much, Pavel. Are there questions? Yes, you. In the back.
Hi, Pavel. Can you say anything about the critical locus if it's not smooth? So is there like some interesting shifted symplectic geometry in that case? Or...
Yeah, so there was a PhD student, Alban Grotalu, who studied this particular case when the critical locus is not necessarily smooth. So what you expect in this case is that there's a Lagrangian correspondence. So there's a critical locus, and then you can look at its kind of symplectic reduction. So there in general, you would expect a Lagrangian correspondence. And I think he has looked at some examples of this setting. So it's...
Tian-Chan.
Hi, thank you. Hi, Pavel. Could you explain a little bit about this one shifted symplectic structure associated to Malin triple?
Yeah. So one way to think about this is, okay, so you have a Lagrangian subgroup. So first of all, D has a non-degenerate pairing. So out of that, you know that its classifying space, so point mod D, has a two-shifted symplectic structure.
Right.
And G inside of D is Lagrangian, so BG inside of BG is also Lagrangian. So now if you look at self-intersection of this Lagrangian, you exactly get this double quotient.
So which should be one less, one shifted.
Exactly, one shifted
Okay,
symplectic.
thank you.
Anyone else? I think there are two comments in the chat window that are still on it. No?
I think they
Oh.
were addressed.
All right.
Yeah.
Anyone else? Yes.
Hey, Pavel, so you mentioned at the end this category MF that you can associate to any, what was it, -1 shifted symplectic scheme with spin structure. So is this a different program than the one that like Roballo, Henny, and Holstein are doing, or is that?
That is that program, yeah.
Okay, great. Sorry.
I think that was it. We will break until 4, and let's thank our speaker again.